Hi, everyone. Welcome to another episode of the Data Standard Audio Experience. My name is Catherine Tao, and today we have Vamsi Chandra Kasivajjala, the co-founder and CTO of Mango Sciences. And today we're going to be speaking about healthcare data. So welcome to the show, Vamsi. I'm so excited to speak with you and learn more about your experiences with healthcare industry.
Thank you so much, Catherine. I'm super excited to be on your podcast. So very quickly about me, as you said, I'm the co-founder and CTO of Mango Sciences. Spent about 21 years in healthcare. My background is computer science engineering. I had the opportunity of building one of the first telemedicine networks in India and later in Africa. Then I went back to India in 2003. Over my career, built about 17 products, over 60 million lines of code, implemented those solutions in thousands of hospitals in 50 countries in 5 continents. Being a serial entrepreneur, I've been involved in 5 mergers and acquisitions and 3 exits so far. So that's my background.
Yeah, it sounds great. And so what are some ways that data really helps predict these clinical outcomes within the healthcare field? I know that healthcare and data, it's constantly changing, but what is your insight on that?
I think it's a phenomenal area, and I think there's no industry which is more exciting than medicine and healthcare in the current scenario. I mean, it's almost like the Renaissance era, where in the 1700s we had these great artists, and the knowledge and the thought process and inventions and absolute works of art that's happening. The same thing's happening right now in medicine. So everywhere you look, you're finding out the Da Vinci's and Michelangelo's everywhere. And one of the greatest things is medicine has been an observational art rather than a science. We still don't fully understand the first principles of medicine yet. And I think the next 2 decades is going to tell us all about the first principles in medicine. And one of the key aspects of that is going to be AI and predicting clinical outcomes, predictive models, and so on and so forth is changing things. And that's quite clear if you actually see the number of these algorithms and models that have been approved by FDA over the last couple of years. You'll see more than 60 or 70 of them have been actually approved for usage in medical setting. And there are a tremendous number of examples that I could potentially give, but I'm going to talk about 2 things. One is patient similarity model or analytics, which is basically understanding the phenotypes. So one of the biggest things is, given the kind of computation power that's available for everyone, and the models itself have become so much better over the last 2 decades. I mean, artificial intelligence, neural networks have been in existence for decades. It's not a new thing, but the changes in the models and the number of people that are working on it and the availability of computational resources have really changed these things. So the ability to understand the key characteristics of phenotypes of patients and bringing them as cohorts, and then from a population health perspective to really understand which group of patients would behave in a particular fashion is extremely critical. And before, when we use the word phenotype, historically the models have been built either using just genomic data or have been built just using clinical data. But now, as a progress, both of these data sets are coming together to give a much deeper understanding as to why patients respond the way they respond to a particular intervention. Could be a medication, could be particular surgery, or whatever that might be. And one of the models that we actually came up with was called patient similarity analytics. It's a temporal view of how potentially a patient would react to an intervention over a period of time. So to take an example, a patient who's diabetic could potentially get other conditions. The disease could progress to give them diabetic retinopathy, diabetic neuropathy, diabetic nephropathy, and so on and so forth. And the ability for us to look at it from a temporal perspective to saying that in time, 3 years down the lane, what is the probability that this patient will actually will have diabetic retinopathy, for example. So today you can actually look at their retinal images, the system, these predictive models can actually say whether the patient has diabetic retinopathy or not. And we actually published a paper in 2014. There was a Kaggle competition around this. We didn't really participate in the Kaggle competition, but that gave us the idea to actually publish that paper independently. Similarly, work in nephropathy and neuropathy and how the patient could potentially get over there. The ability to understand temporally how the patient potentially could reach there. Just think of this as a what if analysis that you're actually doing by changing some of the thousands and tens of thousands of variables in a given patient and saying what would be the best outcome for the patient. And that is your end output. Let's say, how can we ensure that the patient does not progress in their disease, or how can we kind of delay the progress of a particular condition is what we are basically looking at. So it's an interesting area, and a lot of predictive models are being applied in just the example of diabetes that I've taken. One of the key things in that we're doing in Mango Sciences, our platform is called Querent, is actually present, has been implemented in more than 500 hospitals across India, Middle East, and the United States. And we have today over 30 million patients' data, de-identified data, and that's large. We're talking about almost 300 billion data elements, tens of millions of clinical notes, over 400 million lab results, and so on and so forth. Our key focus area is in oncology. And in oncology, the two main areas of PFS, which is progression-free survival and outcome survival. It is extremely critical to understand, to know, for example, immunotherapy, which is one of the key or newer generation therapies, which potentially can stop the progression of cancer in patients. So let's take an example of breast cancer. And though outcome survival is the gold standard, saying that how long will the patient survive? Which is the gold standard. But it's very difficult to find that endpoint because most cancer patients, when they reach stage 4, they would like to, kind of die peacefully along with their loved ones in their own setting at home or something like that, and not really in the hospital. So most cancer or cancer mortalities really don't happen in the hospital, because of which we don't have the data as to when did they die or if they even kind of die. So it becomes very difficult to understand the outcome survival. So one of the key endpoints today for early clinical development to understand the efficacy of different cancer treatments is progression-free survival. So the ability to understand, for just as an example, a tumor size, and how is this tumor increasing in size, or decreasing in size post chemotherapy or surgery, then chemo, then radiation, and then applying and then being on an immunotherapy is an extremely critical model that people are working on. And that has the potential of, these predictive models have the potential to have more and more patients taking up immunotherapies, which would actually help in better quality of life for these patients.
Yeah, definitely. And it sounds like definitely technology and just healthcare in general, it's constantly advancing and growing as the years go by. So it's great that we can see that it's being applied in, like you had said, just chemotherapy and all of these different healthcare needs that people need. And things are just always advancing. So it's great to hear from your perspective as well. And so I know that previously you had mentioned to me about, in a previous conversation outside of the podcast, we talked about NLP. And so how useful it is inside the healthcare industry. So could you talk more about that and elaborate on that?
When we talk about healthcare data, so you have structured data and unstructured data. So most healthcare data actually is the key information is actually in unstructured format. So these are notes. So they can be discharge summaries, they can be clinical notes, progress notes, or could be lab results like histopathology or cytology, lab results, and you have information out there. The ability to extract that information from there is extremely, extremely critical. And what we have observed is that those structured data makes the bulk of the data set, but the more important information is actually in the notes in the unstructured format. And even today, NLP, though there are so many different models that exist, understanding the meaning of these notes from a particular standpoint or what the doctor was really trying to say is extremely critical. And there are too many challenges that are associated with this. The first challenge is that these notes are not structured in a format. Every doctor writes in their own different way. So just to give you an example, a simple word called, or a phrase called coronary artery bypass graft can be mentioned 18 different ways. So they can call it coronary artery bypass graft, a bypass graft, it's called CABG, cabbage, and so on and so forth. So just for a system to understand what these different doctors are saying about the same thing, it's very difficult to do that. So you need to have something like a vocabulary server, or what you call as a WOSR, to really understand these different synonyms. Then the ability to understand and extract and analyze and get to a meaning of what the doctor is really trying to say becomes extremely critical in this. So one of the things that we did was we published this paper called LSTM Dense Merged Hybrid Network for ICD-10 Coding of Clinical Free Text. Way back, this is probably about 5 years ago that we published this paper. So it's a cascaded hierarchical architecture using LSTM. And we compared that with TF-IDF, CNN, so convolution neural networks trained on distributed word embedding and inverted indexing models. And all these complex words, but what it basically does is we took an ontology, and two of the best ontologies which are available today for people to use, for your listeners to, if they want to try it out. One is the UMLS, which is the Unified Medical Language System, and the other one is SNOMED. So they have a lot of the concepts very well embedded over there. So you can actually choose any one of those ontologies. And on top of that, you could start building out your models. So what we do is, today we have now the ability to understand when a doctor writes, like that example of CABG, and we know the system can now understand that, hey, this means coronary artery bypass graft, and it's a procedure, and the CPT code for that is so-and-so. Similarly, if someone basically says that the patient has COPD, which is a chronic obstructive pulmonary disorder, the probable ICD-10 diagnosis for that is so-and-so. And with a tremendous confidence factor, you can actually predict that. So what happens then is this entire coding industry, which is a multi-billion-dollar industry, over a period of time will reduce in size, because the doctors don't have to dictate their notes and then it goes somewhere else, and then there's a human being who's actually typing out all of the converting all of those notes into these structured codes for ICD and CPT, which will then be used for submitting the claims and so on and so forth. All of that would be automated. So there is tremendous effort that's going on, and the kind of models that you will see over the last 3 to 5 years have become so much better. Our own models have more than 95% kind of accuracy, because I can't just give that, because there are also these sensitivity, specificity, and other metrics that we actually look at in the space. But it's in a very generic term, it's super accurate. And that's the way NLP is going, and we believe that it's going to have a huge impact on medicine, and NLP will become one of the mainstays of most healthcare informatics systems over the next decade.
Yeah, absolutely. And I know that you touched on a little bit of seeing how this industry will be changing in the future, but in terms of I know you had mentioned about searching through data elements based on inclusion and exclusion criteria. Could you tell us a little bit more about what this is and what you mean about this?
So one of the most important things for researchers, and that's both in hospitals and outside of hospitals, the medical researchers, is to really understand these cohorts of patients, and they create these disease registries. So let's say, for example, we want to understand about breast cancer, and there are all of these different medications that are available out there to treat patients suffering from breast cancer. But to find the exact set of patients, so for example, there could be a specific immunotherapy medication which only works on, these are receptors called HR negative and HER2 positive receptors. And for that, there is a specific medicine or an immunotherapy medication that's kind of the regimen that's available for them that they could be on. But to find exactly those patients, so these patients need to be obviously women, could also be applied in rare cases in men, but predominantly let's take an example of women post-menopause, HR negative, HER2 positive, and with certain other conditions that are what we call as inclusion criteria. And there'll be a bunch of exclusion criteria that they should not be on. They should not, for example, have a certain set of conditions. Now, to search exactly through these kind of criteria on a normal EHR database is very difficult. And these patients, if you don't find these patients exactly today, then it's very difficult to conduct these clinical trials for these new generation medicines, which the pharma companies are actually innovating to go through their clinical trials. The current process is very manual, globally is very manual. And one of the things that happens is that, just to give you an example, they would go to a bunch of hospitals to find these patients. It's called patient identification. They would manually, these private investigators, the patient investigators would actually go to these hospitals who are going to be a part of this program, in this clinical trials program. They would actually go through all of this data to find these patients. There could be as many as 5 or 10 investigators going through these records for a period of 6 to 9 months to find just these 100 or 200 patients. Now, potentially, that effort can come down to less than a day when you have all of this data using NLP and all of these techniques that we just spoke about. And all of that information is now in a database, and you have the ability to define all of your inclusion and exclusion criteria, and not just based on structured data, but unstructured data using NLP and so on and so forth. So now you can create all of these inclusion and exclusion criteria in a simple screen that you can keep saying that I want this condition and this condition and this condition, but should not have these conditions. Now, if the moment you're able to create these inclusion and exclusion criteria in a system, and you say, search for these patients. Now, like in our system, we have more than 1 million cancer patients. Now, we have the ability to get these exact patients in less than a few hours' time. So what would have been an effort of, over a period of 6 to 9 months' time by 10 different people across so many places, spending 8 to 10 hours every single day, is now something which you can do in less than a day, which is amazing. I mean, that's completely changing and revolutionizing the way the industry is going to work, going forward.
Absolutely. And it's also important to note that there's a lot of people trying to get into the field and the industry as well. And they're still learning about how to handle data, how to get into this data field, and getting the education and the skills necessary to get into this industry. So definitely great insight there. I wanted to thank you so much for being on our show today. It was such a pleasure to speak with you. Where can our community find you online to connect with you?
So you could write to me at Vamsi Chandra at mangosciences.com, or you can search for me on Vamsi Chandra on LinkedIn, and you'll be able to find me there. Would love to work with you guys. So, for example, we have Boston University. We have 16 students from Boston University who are currently working with us as a part of their programs. They're all master's students who are working with us in different areas of NLP. And our chief data scientist, Gavin, is an MIT Harvard guy. He's leading this program. We would love to work with more universities, with more students, with more researchers. And we have different programs where we can give a certain access to our data to work on a certain set of these areas. So would love to have your listeners reach out to me, and I'm sure we'll find some program to work together.
Yeah, fantastic. And to our audience, for more information on the data standard, you can find us at www.datastandard.io, as well as our YouTube and LinkedIn page. And this episode is sponsored by Pandio. They're innovating the tech space with their Apache Pulsar messaging system. So learn more about their work at pandio.com. And thank you so much, Vamsi, for joining us. So great to have you, and such a pleasure to have you on the show today.
Thank you so much, Catherine, and wish you a wonderful day ahead.